In this video, we are now going to take a look specifically at how the transistor is used as an amplifier. This is part 1 of 2 of Transistor Amplifier Operation. We'll first discuss and analyze the operation of one of 3 types of amplifier circuits before moving on to multi-stage amplifiers. This is the most basic amplifier circuit that you can already use. This linear amplifier amplifies the input signal V sub S and the output VCE taken at the collector terminal. Note that the subscripts are small letters indicating that these are AC signals. The values indicated are always RMS values unless otherwise specified. RMS values are used because this is the quantity that is directly measurable by a multimeter. Immediately, we see our voltage divider bias with resistors R1 and R2. We can also see 2 capacitors C1 and C2. C1 capacitively couples the input signal V sub S to the input base voltage across R2. C2 capacitively couples the output voltage at the collector terminal to the load resistance RL. The role of capacitively coupling is to allow AC signals to pass while blocking the DC signal. Thus, C1 prevents DC biasing from the internal source resistance to the voltage divider bias, while C2 prevents DC biasing from the load resistance to the already present DC bias voltage at the base and at the collector. These capacitors appear as shorts to AC signals but appear as open switches to DC signals. Let's now take a look at how amplification is achieved. The voltage divider bias transistor circuit operates at its Q point, which is the zero level of the input signal. In the first half cycle, the input voltage increases above the Q point. This increases the base current at the base terminal. This translates to an increase in the collector current at the collector terminal. Recall that the output voltage VCE is just the difference between VCC and the voltage across the resistor RC. Thus, subtracting ICRC from VCC gives an output that is below the Q point. In the second half of the cycle, the input voltage is below the Q point, and this is seen as base current that is also below the Q point. It is amplified as IC at the collector terminal. Subtracting ICRC from VCC gives an output that is above the Q point. Thus, the final output is 180 degrees out of phase with the base voltage. This is called phase inversion. If we take a look at the transistor load line, we can appreciate more how the phase inversion works. The Q point is indicated along the load line. The input signal is indicated as the red sinusoidal curve, while the output signal is the blue sinusoidal curve. At the Q point, the base current is amplified as the collector current. Projecting the collector current to the load line at the Q point gives us the collector emitter voltage. If the input signal is above the Q point, the projection along the load line is a signal below the Q point along the VCE axis. If the input signal is below the Q point, the projection along the load line is a signal above the Q point along the VCE axis. The table shows the different parameters used in analyzing transistor amplifier circuits. We already know about DC alpha and DC beta. We have been using DC beta extensively. DC alpha describes the ratio of the DC collector current to the DC emitter current, which is between 0.95 and 0.99. In this table, AC alpha and AC beta are similarly defined as the ratio of the AC collector to the emitter currents and the ratio of the AC collector to base currents, respectively. R sub E prime is the AC emitter resistance. R sub B prime is the AC base resistance. R sub C prime is the AC collector resistance. For amplifier analysis, the AC emitter resistance is the most important of the R parameters and is given as shown. R E prime is approximately equal to 25 millivolts divided by the DC emitter current. Note that the AC emitter resistance is computed from the DC emitter current as symbolized by the capitalized subscript. The difference between the DC beta and the AC beta parameter is shown in the figure. The DC beta parameter is computed at the value of IC and IB Q point with respect to the origin of the IC versus IB curve. On the other hand, the AC beta is more dynamic and changes depending on where the Q point is. It can be computed as the slope of the tangent line at the Q point in the IC versus IB curve. The first type of transistor amplifier circuit that we're going to learn is the common emitter amplifier. This circuit is shown in the figure. You've already seen this circuit as we've already studied this before in the previous slides. There's just one minor addition, and that is capacitor C2 that is parallel to the emitter resistance. This capacitor is called the bypass capacitor and couples the emitter terminal to ground. As we've already learned, the input current at the base terminal is amplified at the collector terminal, and the output signal is taken at the collector terminal, which we call VCE. Strictly speaking, it is not VCE, but VC, since there's an emitter voltage present due to the emitter resistance. In other words, VCE must be equal to the difference between the collector voltage VC and the emitter voltage VE. By coupling the AC signal at the emitter terminal to ground, then the effect of the emitter resistance is removed, and the AC emitter voltage is just zero. Thus, VCE is just equal to VC. This is why C2 is called the bypass capacitor, because the AC signal does not pass through RE but goes through C2. If that is the case, why would we still need RE? Why not just remove it? Well, we still need it to define the Q point. In order to get the Q point, we need to analyze the voltage divider bias of the transistor. We analyze this using the Thevenin equivalent circuit discussed in the previous slide. We first solve for the RTH, which we obtain as 5.19 kiloohms. Next, we solve for the Thevenin voltage and obtain a value of 2.83 volts. We can solve for IE next, which we find to be 3.58 milliamperes. Since IC is approximately equal to IE, then IC is also 3.58 milliamperes. This is one coordinate of the Q point. We then obtain the emitter voltage as having a value of 2 volts. Next, we get VC, which is the difference between VCC and the voltage across the collector resistor, with a resulting value of 8.42 volts. Finally, the last coordinate of the Q point is obtained from the difference between the collector and emitter voltages, with a value of 6.42 volts. Note that the input base resistance is computed to be 11.3 kiloohms and is quite comparable to the value of R2. This means that we are justified in using the Thevenized equivalent of the voltage divider bias circuit for the transistor. You can also see from this analysis the significance of keeping the emitter resistor in determining the Q point. Now that we know the Q point, let's analyze what is happening to the AC signal. The figure shows the equivalent circuit as seen by the AC signal. The green shaded region is the AC source, while the dirty white shaded region is the equivalent circuit as seen by the AC signal. Compare this briefly with the original circuit. We observe two things. The capacitors C1, C2, and C3 are replaced by their effective shorts. Since C2 shorts the emitter terminal to ground, the emitter resistance has no effect. These capacitors are selected so that the capacitive reactances are negligible at the signal frequency and can be considered 0 ohms. The second thing that we notice is that the resistors R1 and RC, which were originally connected to VCC, are now connected to ground. In other words, the DC source is replaced by ground. The DC voltage source has an internal resistance of 0 ohms as seen by the AC signal, since it holds a constant voltage independent of the load. Thus, no AC voltage develops across it so that it appears as an AC short. This is why a DC source is called an AC ground. In some sense, you can think of a DC source as a capacitor that capacitively couples the AC signal to ground. After all, what is a voltage source but a charged capacitor? To analyze the circuit, we represent the impedance of the transistor circuit as the input base resistance, R in base, shown in the upper right figure. The total input base resistance, R in total, is therefore just the equivalent parallel resistance of resistors R1, R2, and the input base resistance. The base voltage is then given by the voltage divider equation as shown. If there is no source resistance, then the base voltage is just equal to the source voltage. What about the input base resistance? The input base resistance is just equal to the base voltage divided by the base current. The base voltage is defined in terms of the AC emitter resistance as shown. Since the collector current is approximately equal to the emitter current, then the base current can be expressed in terms of the AC beta parameter. We then use our new expressions for VB and IB to get the input base resistance. The input base resistance is simply the AC beta parameter multiplied by the AC emitter resistance. What about the output resistance? We still need to know the output resistance because we will need it to solve for the voltage gain later. The output resistance is given by the equivalent parallel resistance of the collector resistance and the AC collector resistance as shown. However, the AC collector resistance is typically much larger than the collector resistance, so that the output resistance, for practical purposes, is estimated to be equal to just the collector resistance. We can now solve for the voltage gain of the amplifier. The voltage gain, A sub V, is defined as the output voltage divided by the input voltage. The output voltage is measured across the collector resistor. Since the collector and emitter currents are about the same, then the output voltage is just the product of the emitter current and the output resistance, which is just the collector resistance. The base voltage has been computed to be the product of the AC emitter resistance and the emitter current. Thus, the voltage gain is just the ratio of the collector resistance to the AC emitter resistance. Note that this gain is obtained from the ratio of the signals at the collector terminal with respect to the base terminal. In order to get the overall voltage from the source to the collector, we consider the attenuation of the input signal voltage to the base voltage. The attenuation is the inverse of the gain and describes the decrease of the voltage signal. The overall voltage gain is given by the gain or attenuation from the source to the base terminal and the gain from the base terminal to the collector terminal. The expression is shown. Let's reanalyze this circuit focusing on the effect of the bypass capacitor. We can compute for the impedance Xc of the capacitor C2 knowing the frequency of the input signal. As a rule of thumb, we select the capacitor value such that the emitter resistance must be greater than or equal to at least 10 times the capacitive reactance of the bypass capacitor. What if the bypass capacitor did not satisfy this condition? How would this affect the voltage gain? In this case, the AC signal would also pass through the emitter resistor and there would be a voltage drop across it. Thus, the effective resistance from the base terminal, as seen by the AC signal, is the series resistance of the AC emitter resistance and the emitter resistor. Since RE is typically larger than the AC emitter resistance, the voltage gain decreases significantly without the bypass capacitor. Let's now try to solve for the voltage gain of the circuit we have been using since the beginning of this video lecture. We've already determined the Q point earlier. To solve the overall voltage gain, we would need to evaluate the AC emitter resistance. We also need to determine the total input resistance. If we assume that the source resistance is 300 ohms, then we can solve for the overall voltage gain. The AC emitter resistance is computed using the DC emitter current, which we already determined to be 3.58 milliamperes. Thus, its value is 6.98 ohms. We can then determine the voltage gain from the base terminal to the collector terminal. The gain is then 143. To get the attenuation, we need to solve for the total input resistance, which is the equivalent parallel resistance of R1, R2, and the input base resistance. We already determined the input base resistance to be equal to the AC beta parameter times the AC emitter resistance. Plugging all of these in, we then solve for the overall voltage gain to be 108. We haven't checked whether C2 is a good bypass capacitor satisfying the condition where 10 times the capacitive reactance must be less than or equal to the emitter resistance. At this point, we don't know the operating frequency. However, we can rewrite the equation in terms of the frequency f to determine the range of frequencies that satisfies this condition. Plugging in the given values for RE and C2, we see that the frequency must be greater than 284 Hz, which is a very good range since it can be used to practically any frequency except frequencies below 284 Hz, including the 50 or 60 Hz line frequencies and its first couple of harmonics. If the frequency is below 284 Hz, the alternate expression for the voltage gain, which includes the emitter resistance RE, must be used. Now, let's take a look at the effect of the load resistance RL. We know that the resistor RC is connected to ground as seen by the AC signal. Since the resistor RL is connected to ground, RC and RL are parallel to each other. Thus, the new voltage gain from the base terminal to the collector terminal will be in terms of the equivalent parallel resistance RC with a small c, which is just equal to the expression shown above. We can now see that the voltage gain is reduced since the equivalent resistance R small c is less than the DC collector resistance. However, if we choose a load resistance much larger than the collector resistance, the equivalent resistance R small c is approximately equal to the DC collector resistance, and the load will have very little effect on the gain. There's one final note we need to discuss about the AC emitter resistance. The AC emitter resistance, as we've seen, is dependent on the DC emitter current. It is also dependent on temperature. Therefore, stability of the voltage gain is an issue. It is good practice to typically add a second emitter resistor at the emitter and just before the junction, connecting the original emitter resistor and the bypass capacitor. This method is called swamping and is used to minimize the effect of the instability of the AC emitter resistance without reducing the voltage gain to its minimum value. The addition of the emitter resistance swamps out the effect of the AC emitter resistance on the voltage gain. Thus, the denominator in the expression for the gain will have an additional term RE1. Typically, RE1 is a few times larger than the expected stable value of the AC emitter resistance. If RE1 is at least 10 times, then the denominator in the expression for the voltage gain is just given by RE1. The addition of the resistor RE1 also changes the input base resistance by adding the value of RE1 to the AC emitter resistance as shown. Let's now consider this example. In this example, we need to determine the DC collector voltage, the AC collector voltage, and then draw the total collector voltage waveform and the total output voltage waveform. We have a voltage divider circuit powering our transistor. Now the input voltage is 10 millivolts, operating at some frequency f. The source resistance is 600 ohms. C1 is 10 microfarads, C2 is 100 microfarads, and C3 is 10 microfarads. The load resistance is 47 kilo ohms. The voltage divider resistors are R1 equals 47 kilo ohms and R2 equals 10 kilo ohms, and the collector resistor is 4.7 kilo ohm. We have two resistors at the emitter for swamping the effect of the AC emitter resistor. The resistor RE1 is 470 ohms and the resistor RE2 is also 470 ohms. Our DC source is 10 volts. We first solve for the Thevenin resistance. And using the equation, we get 8.25 kilo ohms. We then solve for the Thevenin voltage and we get 1.75 volts. The emitter current is obtained using this expression and is equal to 1.06 milliamperes. Since the emitter current and the collector current are approximately equal, the collector current is also 1.06 milliamperes. Now VE, or the emitter voltage, is obtained by multiplying the emitter current by the sum of the emitter resistances. Since there are two emitter resistors, RE1 and RE2, the total resistance is 940 ohms, and thus VE is equal to 1 volt. Now VC is equal to the difference between VCC and the voltage across the collector resistor. And this is equal to 5.02 volts. Now VCE is equal to VC minus VE, which gives us 4.02 volts. So our Q points are VCE equals 4.02 volts and IC equals 1.06 milliamperes. Notice that the input base resistance, using the equation, gives us 240.6 kilo ohms, which is much greater than 10 times the resistor R2 or 100 kilo ohms. So it may not be necessary to Thevenize the circuit in this case. Now let's determine the AC collector voltage. The AC collector voltage is obtained beginning with the determination of the AC emitter resistance. The AC emitter resistance is given by the expression 25 millivolts divided by the DC emitter current, and the result is 23.6 ohms. The collector current, or the collector resistance with a small c, is obtained using the expression and is given by 4.27 kilo ohm. The voltage gain from the base terminal to the collector terminal is then equal to 8.6. The input base resistance is equal to BAC times the sum of the AC emitter resistance plus RE1. Remember that we need to include RE1 in this case because this RE1 is not parallel to C2 and therefore the AC signal sees this resistance. Thus input base is equal to 86.5 kilo ohms. The total input resistance is therefore 7.53 kilo ohms. Now the overall voltage gain is thus equal to 7.53 kilo ohms divided by 600 ohms plus 7.53 kilo ohms times the voltage gain from the collector, from the base to the collector, which is 8.6. Thus the overall voltage gain is 8.0. Since the overall voltage gain is 8.0, if we multiply that by the input voltage of 10 millivolts, we expect that the output voltage is 80 millivolts. Now, our Q point was determined to be 1.06 milliamperes, and 4.02 volts. In the book, VCE was not determined, but it should have been. This should be the median value or the DC value superimposed with the output AC signal, and not the 4.74 volts as you see in the figure. The positive peak voltage is 80.0 millivolts times square root of 2 plus VCE, which is equal to VCE equal to 4.02 volts. This should be equal to the total of 4.13 volts. The negative peak voltage is VCE minus 80 millivolts times the square root of 2, and the value should be equal to 3.91 volts. At the load, the output voltage filters out the DC signal, and what's left is the AC output voltage with a peak voltage of 80 millivolts square root of 2 or 113 millivolts. The source voltage has a peak voltage of 10 millivolts times the square root of 2 or 14 millivolts. Now, we can connect one or more amplifiers in sequence, resulting to a total voltage gain, which is the product of the individual gains. This is called a multi-stage amplifier. The expression for the overall voltage gain is shown. Oftentimes, the voltage gain is expressed in dB units. The expression to convert the voltage gain to dB is also shown. Here's an example of a two-stage common emitter amplifier. It's basically our voltage divider transistor amplifier connected in series. Notice that the output of the first stage is capacitively coupled to the input of the second stage. You will also notice that regardless of the number of stages, we need only one power source, VCC. If you recall, for a single-stage amplifier, the voltage gain is obtained from the ratio of the collector resistance to the AC emitter resistance as shown. In this case, RC is equal to R3. However, the AC signal at the collector terminal sees R5, R6, and the input base resistance of the second stage amplifier is connected to ground. The voltage gain for the first stage is then written as shown. For the second stage, there's no load resistance. Then RC is equal to R7. Thus, the total overall gain is the product of these individual voltage gains. This is the second to the last lecture video for this topic. The last video lecture will tackle the other types of operation of the transistor amplifier and the differential amplifier. You'll see a few exercise videos in the next activity. After that, you should try to solve a few exercises on your own and have them checked during our consultation sessions before taking on the third exam.